Okay, welcome back. Let me open up my screen here. All right, so we've been looking at these design patterns, and today I want to cover one that I find particularly interesting. And let me close off all this stuff here. Um, here we go. Okay, the design pattern that we're going to talk about today is the state design pattern, okay? And when it comes to state, you remember we looked at the state changes of a particular object at runtime, and we had this UML diagram that showed the states. So here we're looking at the state changes of an object that represents a college class. Okay, so at runtime, it goes through a number of states. Okay, now there's a design pattern, especially for implementing these state changes, and that is, of course, the state design pattern. Okay. Oh, before I launch into the state design pattern, are there any questions about any of the previous patterns that we've talked about? I know the examples were all kind of contrived, but they were designed to be simple so that that you didn't get they were designed to be simple so that the design pattern didn't get lost in a lot of details. Okay, and then here for the state design pattern, of course, we'll have yet another contrived example. Okay. All right, any questions at all about any of the previous patterns? Okay. All right, well, as I've said many times, these design patterns are kind of the top of the ladder when it comes to doing good design. We've gone from design principles to design patterns, and of course the patterns are based on the principles. Okay? All right, so the state design pattern helps objects control their behavior by changing their internal state. Okay, so as an object changes state, its behavior will change, depending on what state it's in. Okay, so our contrived example is going to be we're going to model a gumball machine. Okay, and the gumball machine will be in various states, and each state will have certain behaviors for the gumball machine. Okay? All right, so here's a gumball machine, and these circles here represent the states. Okay, so a gumball machine, it could be out of gumballs. It could have a quarter, meaning that somebody has put in a quarter into the gumball machine. It could be in a state where there's no quarter, nobody has put in a quarter into the machine. And this is a state where the gumball machine is selling a gumball. Okay. Now these arrows here, of course, are the transitions from one state to another, and then the labels on the arrows are the events or triggers that cause a state transition. So, for example, if the gumball machine has a quarter, and the action is to turn the crank, then of course we transition to having sold a gumball. Okay, and if there's a quarter in the machine and it ejects the quarter for whatever reason, then we go from the has quarter to the no quarter state. And if you're in the no quarter state and somebody inserts a quarter, then of course you go from the no quarter state to the has quarter state. Okay. After a gumball is sold, either you go back into the no quarter state, waiting for somebody to put in another quarter, or you might go to the out of gumball state in case you just sold the last gumball. Okay. So this is the idea. We're going to have a gumball machine object, and it has these 4 states, and it has these transitions from one state to the next. Okay, And so we are going to write code that simulates the behavior of this gumball machine, and then we'll come up with an initial design, which seems okay, but then we'll point out problems with that design and show how if we use the state design pattern, it will greatly improve our design. Okay. All right. So that's what we're going to try to do. And first thing we have to do is to gather up the states. So we go back to this diagram. We saw there were 4 states. So here they are. Okay. And then if we're going to model this object, then here are the 4 states: sold out, no quarter, has quarter, or sold. Okay. Sold out, has quarter, no quarter, and so forth. Okay, so here are the 4 states, which in this Java code is being represented by constants. But of course, if we're writing in C++, we would do something like this, right? We would have an enum class, and these are the 4 enumeration constants. Okay? All right, now when we first create the gumball object, gumball machine object, we're going to put it in the sold out state, just to initialize everything. Okay. All right. And here are the actions that will cause us to make a transition from one state to the next. And so if we go back to this diagram, you can see here are the actions: turning the crank, ejecting a quarter, and so forth, dispensing a gumball. And so those are the actions that will cause us to make a state transition. Okay. As you can probably imagine, these actions are going to turn into functions. Okay, so when we call the turn crank function, we'll dispense a gumball and then make a transition to another state. Okay, so here are the actions. Okay, all right. Now we're going to create a state machine class, and for each action, we're going to have a function, as I said. Okay, and each function will have a bunch of if statements to test what is the current state, and depending on what the current state is, then it will take the appropriate action for that function. Okay, so the conditional statements will determine what behavior is appropriate in each state. Okay, so here we go. Here's the insert quarter function. Okay, now if we call insert quarter, what are we supposed to do? Okay, well, if the current state of the gumball machine is already in the has quarter state, then the action is to print out, hey, you cannot insert another quarter, because obviously there's already a quarter in there. Okay. Now, if the current state is no quarter, then of course inserting a quarter will then change the state to has quarter. Okay. If the current state is sold out, then it's going to say, well, you can't insert a quarter because there are no gumballs. Okay. And if the current state is sold, meaning that you've just sold a gumball, then you can say, hey, we're already giving you a gumball, don't put in another quarter. Okay. So the important thing here is with insert a quarter, okay, there is going to be a state transition from no quarter to has quarter, assuming that the current state is no quarter. Then when you insert a quarter, you make that transition to has quarter. And that's what we're seeing here. Okay, so if the current state is no quarter, then you make the transition. Okay, and okay, so that's the action. Insert quarter, and what actually happens depends on what state the gumball machine is in. Okay, all right, is this clear? Right. So this is the way we're designing the code. And then here is, oops, did I go the wrong way? Okay, so here, uh, uh, when we initialize the gumball machine, okay, this is the default constructor. Okay, remember initially the state is sold out, and then when we call the default constructor for the gumball machine object, we pass an account of how many gumballs there are in the machine, and we go ahead and initialize count. And if the count is greater than 0, then we then say, okay, the state really ought to be no quarter, meaning that the machine is waiting for somebody to put in a quarter. Okay. All right. Otherwise, if we start out with 0, then we stay in the sold out state. Okay. Presumably, when we construct a gumball machine, we give it a positive number for count. Okay. All right. So okay. Well, you already saw insert quarter. Okay. Again, depending on what state you're in, you have a certain behavior for inserting a quarter. And one important one is that if the current state is no quarter, we do change state to has quarter. Okay. Now here's eject quarter. Okay. Now of course you cannot eject a quarter unless you already have a quarter, and that means you were in the has quarter state, and so you print out a message saying that you're returning a quarter, and then you transition to the no quarter state. Okay. Now, if you're already in the no quarter state, it doesn't make sense to eject the quarter, and so you print out a message saying, hey, you haven't inserted the quarter. If you're already in the sold state, meaning that you've already sold a gumball, then of course you can't return the quarter because that person's already returned the crank. Okay, and if you're in the sold out state, then you haven't inserted a quarter, and so you print out a message saying that. Okay, so the only behavior that makes sense when you call eject quarter is if you are already in the has quarter state, then you can return the quarter and then transition to the no quarter state. Okay, and all the other if you're in any of the other states, that's trying to eject a quarter is really doesn't make sense. Okay. All right, that's eject quarter. Turning the crank. Okay. Well, the only time that makes sense is if the current state is has quarter, and then you say, okay, we're going to transition to the sold state, and then of course dispense a gumball. Okay. And then all the other states, well, it doesn't make sense to turn the crank. If you've already sold a gumball, then turning the crank twice doesn't get you another one. If you're currently in the sold out state, then of course you cannot dispense any gumballs. Okay. All right. So these are the possible behaviors for turning the crank depending on what state the gumball machine is in. Okay, and I think there's one more dispense. Okay, so this is the dispense action, and that only makes sense if you are in the sold state. Okay, and so there you dispense a gumball. Decrement the count by 1. If the count is now 0, then you go into the sold out state. Otherwise, if there are still more gumballs in the machine, you just go into the no quarter state, meaning that you're just waiting for somebody else to put in a quarter. And all the behaviors for all the other states, again, don't make a lot of sense. If you are in the no quarter state, then of course you haven't paid yet. If you're in the sold out state, well, there's no gumballs. And if you're in the has quarter state, then you print out that, hey, no gumball was dispensed. Now the comment here, is that these should never really happen, and we can see why, because we call dispense only when we are in the has quarter state. And so I guess for completeness, we go ahead and write code for each of the other states. Okay. All right. So is this making sense, or is this design making sense? Right. So we have an object, the gumball machine object. It can be in any one of 4 states. There are a number of actions that we can take on the gumball machine, and what behavior actually occurs depends on what state the machine is in. So for each of the actions, okay, like turning the crank, we have to consider what to do for each of the states. Okay, so you see, for each action, we've had to then check what state we're in. Okay. All right, so here is a test program, and I actually have rewritten this example in C++, and we could take a quick look at it. But you can see a test program just basically goes through a number of actions. It's a little hard to see. Okay, we go ahead and create a gumball machine with 5 gumballs. We print out the current state of the machine, or how many gumballs there are in there. We insert a quarter, turn the crank, insert a quarter, eject a quarter, and turn the crank. And so here, the test program just goes through several sequences of actions, and then we want to see if the gumball machine behaves properly depending on the current state it's in. And then, of course, you saw that some of the states, some of the actions cause the gumball machine to change state. So therefore, that will affect any subsequent actions. Okay. All right. So this is our design, and let me just quickly show you how I translated all that into C++. Now the language really is immaterial. I mean the whole idea is getting all the various states and behaviors proper when you do the actions. So here are the states that the gumball machine can be in. Okay. And here are the actions that can take place. Okay. So it turns out there are 4 states and 4 actions, but yeah, that's just coincidence. When we initialize the gumball machine, we give it a count. Okay. And then I overloaded the output operator just to print out the current state of the gumball machine. Okay. So here's gumball machine.h. And here is the code, and this is basically the code that you saw earlier. Here's insert quarter, and then depending on what state we're in, we have certain behaviors. Okay, so and then the important one here is I guess inserting a quarter. Oh yeah, if we were in the no quarter state, then of course inserting a quarter is going to change us to the has quarter state. Okay, and then for the other states, inserting a quarter doesn't make sense. Okay, here's ejecting a quarter, and of course that makes sense only if you are in the has quarter state, and then you transition to the no quarter state, and then turning the crank here. That only works if you're in the has quarter state, because you can only turn the crank if you've already put in a quarter, and then we transition to the so state and call dispense, and then dispense actually dispenses the gumball and updates the count, and depending on the count, we either go into the sold out state or the no quarter state. Okay? So that that's basically the code. And then I overloaded the output operator to output a gumball machine, and that just prints out the current state and how many gumballs are left in the machine. Okay. All right, so this is the test drive. Okay, let me see if we can do this properly. Okay, so I'm going to run this gumball machine test drive. Okay. And okay, there we go. So we start out with 5 gumballs, and the machine is in the waiting for quarter state. Okay? Remember, that's how we initialize it. When there are gumballs, we go ahead and insert a quarter and turn the crank, and we get a gumball. Yes. Okay. And now we have only 4 gumballs left. Okay. And we've gone back into the waiting for quarter state. Okay, so here we are waiting for a quarter. And now I insert a quarter, and then I eject the quarter. So I insert the quarter, and sure enough, I got my quarter back. But then if I try to turn the crank, because we're in the no quarter state now, then we get this error message. Okay. All right. And okay. Quickly here. Okay, now we still have 4 gumballs. We're in the waiting for quarter state. Okay, we insert a quarter, turn the crank. Okay, insert a quarter, turn the crank. We get a gumball. Okay, we insert another quarter and turn the crank. Okay, and we get another gumball. Okay, so we got 2 gumballs this time, and then we try to eject the quarter. And of course, we can't do that because there are no quarters in the machine now, and so we get this error message. Okay. All right, now we're down to 2 gumballs. Okay, and we're back into the waiting for a quarter state, and you can see here now we insert a quarter. Okay, we try to insert another quarter, and we can't do that. Okay, because we're already in the has quarter state. We turn the crank, we get a gumball. Great. Okay, we insert another quarter, turn the crank again, and we get a gumball. Now we're out of gumballs. Okay, and then we finally try to insert another quarter, and we don't allow that because the machine is now empty, and turning the crank doesn't do any good, okay, because there are no gumballs. Okay, all right, so that was a simulation of our gumball machine using state transitions, and depending on what state the machine is in, it has different behaviors for the various actions. Okay? All right, any questions at all about this program? Okay, so of course, this is our first design, and as usual, we're going to point out difficulties or problems with this design, and then show how a design pattern comes to our rescue, and we end up writing a much better program that is more flexible and reliable and encapsulates changes and so forth. Okay. All right. Any comments at all about this program? Okay. I suspect that this is the kind of program that most of you and probably I would have written initially, because it just seems like a logical thing to do. We have states, and we have actions, and what happens, what behavior we see from each action depends on what state we're in. Okay. All right, and any comments? Okay. All right, well, let's start seeing what's wrong with this solution, and then we'll see if we can improve it. Okay. All right, so now, of course, many times our design shows its problems when there are changes, right? Change and complexity, those are our two big challenges when we're doing software design. Okay, so here's the CEO of the Gumball company, gumball machine company, and he wants to make a change so that 1 out of every 10 gumballs sold can be a winner. Okay, so 10% of the time, when you turn the crank, you'll get 2 gumballs instead of 1. Right? So he wants to make that change. He thinks he'll add a little more excitement to his product and maybe end up selling more gumballs. All right, well, given our current design, how can we accommodate this change? Okay. All right, so we had these 4 states initially, okay, and so now we need to add a 5th state called winner, right? But then that means that for each of these functions, we need another if statement, right? Because remember, each of these functions tested with if statements what state you're currently in, okay? And so now we added, if we add a 5th state, that means we have to go through each of these functions and add yet another test. Okay. All right. So and then it points out here that turning the crank will be especially messy, because turning the crank is where it's possible that if we're in the highest quarter state, we dispense a gumball, but now 10% of the time we have to dispense 2 gumballs. Okay, so turn crank, besides adding an extra test to see what state we're in, the dispense, the actual dispensing code will have to then check to see if you should be a winner and give you 2 gumballs instead. Okay. All right. So what this is pointing out is that we're having trouble extending the code. Okay. We've added a new requirement, and look, that change is rippling throughout our code. We're going to have to make a change to each and every one of these functions. Okay. And that's not good. We have not encapsulated very well the change. Okay? Okay, so here's the new design. Okay, we're going to define a new state interface that contains a function for every gumball machine action. So up until now, the state was represented by either in this Java code an integer constant, or in the C++ code, the state was represented by the enumeration. Okay, remember what I had here. Okay, okay. So this is how we were representing the state. Okay, just basically a constant. Okay, and so in our new design, state will be represented by an object. Okay, so we're going to have state objects. Okay, okay, and so state will be a superclass. It's going to represent all the states, and then each of the states of our gumball machine will be a subclass of state. Okay, and then remember that the superclass will then have each of the 4 actions. Okay, so that means that each of the state subclasses will have to implement those actions. Okay, okay, all right. So what we were going to do then, remember that in our initial design, each of the functions had all those had those if statements on there to test what state we're in. Okay, this design will get rid of all those if statements. Okay, and so you'll see how that happens. Okay. All right, so here again is our state superclass, okay? And you can see it has the actions, okay? They are abstract functions so that, okay, we have to implement these functions in each of the state subclasses. So here's the sold out state, and you can see it implements all 4 of the actions. The sold state, here's the sold out state, no quarter state, and has quarter state. Okay, so for each state that the gumball machine can be in, we're going to have one of these subclasses. Okay, and then each subclass implements the action. Okay, all right, are we okay so far? All right, here we go. Okay. Okay, so instead of what we had initially, where the states were represented by a constant, we now have these 4 state subclasses. Okay, sold out state, no quarter state, etc. Okay, we're looking at these guys down here. Okay, and the initial state, of course, will be the sold out state. Initial count again will be 0. Okay. Okay. Now. Here's the gumball machine. It's got the 4 states that it could be in. Okay, and here we are going to initialize the gumball machine object number. We're passing in the number of gumballs, and here we are. Oops, actually, sorry, I just touched that mouse the wrong way. It does that. Here we are creating the 4 state objects, and here, if the number of gumballs is greater than 0, we initialize state to no quarter state. Otherwise, we initialize state to sold out state. Okay, so there are no gumballs. We are going to be in the sold out state. But normally, we are going to pass in a positive number of gumballs, so the initial state will be the no quarter state, meaning that we're waiting for somebody to put in a quarter. Okay. All right, and okay. Now here, I'm showing you that when we have each of these functions here, okay, we then say, well, we're going to call the insert quarter, because when we call the insert quarter function, okay, we're going to delegate the actual behavior to the current state. Okay, so whatever the current state is, it's going to handle insert quarter. Okay, when we call the reject quarter function, whatever the current state is, it's going to handle the eject quarter. Okay, and here's turning the crank. Turning the crank says that, okay, whatever state we're in, we're going to have that state deal with turning the crank, and have that state deal with dispensing. And then you can see here that we can change state. Okay, here's a setter for the current state, and we pass in the new state, and then that changes the state of our gumball machine. Okay, and then here's the helper functions to release the gumball. Okay, all right. So now that says that whenever we try to do an action on the gumball machine, such as inserting a quarter, okay, the behavior depends on the current state, just as before, okay, but now it's a state object, okay, that we delegate the action to, and you can imagine that because of polymorphism, we're going to then invoke the appropriate insert quarter function depending on the current state. Okay. All right, so let's take a look at how that works. Okay, okay, here's a no quarter state. Okay, and it's a subclass of state. Okay, excuse the Java code here, but this basically says that class no quarter state is a subclass of state. Okay, now therefore it has to implement each of the abstract functions, right? So here, okay, well, here we are. This is the constructor for the no quarter state, and basically is setting the gumball machine, or is initializing is pointed to the gumball machine. Okay, so each state object will have a reference to the gumball machine, and that's what the constructor is doing here. Okay, all right. So how does a no quarter state implement the insert quarter action? Well, it prints out the message and changes the state of the machine to the has quarter state. Okay. Okay. Here we are implementing eject quarter. Well, if we're in the no quarter state, then we cannot eject the quarter, we cannot turn the crank, and we cannot dispense a gumball. Okay. So these are the behaviors that we're going to implement for the no quarter state. Okay. And then here are the behaviors that we will implement for the has quarter state. Okay, so again, we initialize the reference to the gumball machine. If you're in the has quarter state, then that doesn't make sense to insert another quarter. Okay, you can eject the quarter. Okay, and then of course the gumball machine then has to transition to the no quarter state. So here's the set state call. Okay, if you're in the has a quarter state, then of course turning the crank will allow you to get a new gumball, and we're going to change the state of the machine to the sewed state. Okay, and then here we say that we can't dispense. Okay. Now the sewed state, then we can dispense. So here, if we are in the sewed state, we can dispense a gumball, and so here's the code to release the gumball and update the count of gumballs and so forth. Okay, and then each of the other actions when you were in the sewed state don't make sense. So we just write out an error message. Okay, so this is the sewed state, and okay, I guess that took care of. Let's see, there's a no quarter state, has quarter state, sewed state. Let's see, what? Oh, I guess I didn't do the sold out state. Okay, well, there's also a sold out state. Okay. All right, so assuming that we have implemented all four of the states, okay, what have we done? Okay, we basically refactored the code. Okay, the program will work the same way as in the previous version. Okay, but we have completely changed the architecture of the program in a way that we hope is an improvement. Okay, so when we refactor code, we are not changing how the code behaves, but we are improving it somehow, and hopefully, well, you want to make those improvements without changing the public interface, so that any other code that depends on the code that you're refactoring doesn't have to be rewritten after you've done the refactoring. Okay, refactoring basically says you're going to change the internal structure of the code to make it better somehow, but the callers, the users of that code, should not see any difference in terms of the interface. Okay, so we've localized the behavior of each state into its own class. And so, for example, the has quarter state takes care of all the behaviors for being in that state. Okay, all those if statements disappeared. Okay, remember in our first version we had for every action, we had to do all that testing to see what state we're in. Well, now we know what state we're in because we're using that particular state object that tells us what state we're in. Okay. We've closed each state for a modification. Okay. However, we can still extend the program by adding new states. Okay. Okay. And now that the code base and the class structure actually more closely resembles that diagram that I showed you in the beginning. This diagram. Yeah. So the code actually more closely resembles this because now we have each of these states is a separate class. And depending on what class we're in, when we try to do one of the actions, the class determines what action to take. Okay. All right, so we have restructured the code. Okay, let's see, where were we? We were, okay, solid states, we refactored. Here's what we managed to do. And here's how the code now works. Okay, we have the gumball machine, and it always knows what its current state is. Remember, there's that state variable that says what state we're in. Okay, so here, this says the current state is has quarter. Okay, here are the 4 states. Okay, now given that we are in the has quarter, okay, when we turn the crank, okay, well, the code for the has quarter state tells us that we're supposed to transition to the SOD state, right? When we turn the crank, and so now the gumball machine is going to be pointing at the SOD state, okay? And when we take an action, it's going to be the SOD state object that determines what the behavior is, okay? Okay. So no more testing what state you're in, okay? Whatever state you are in determines the behaviors when you call any of the action functions. Okay. So now we've made the transition from the has quarter state over to the SOD state. Okay. And so that's basically how this thing will work. The gumball machine will have this current state pointer pointing at any one of the 4 states, and the current state determines the behavior. Okay? So that is the state design pattern. Okay, so the state design pattern allows an object to alter its behavior when its internal state changes. And so the object will appear to change its class. And so here is the gumball machine class, and how it behaves at runtime depends on its current state. And so it appears that the gumball machine itself has changed, but really what has changed is the current state, and the gumball machine's behavior has been delegated to the current state. So as the states change, it appears that the gumball machine itself is changing. Okay? So that's an interesting illusion that this design pattern produces. Okay, so the object appears to change its class. Okay. Okay, so what we've actually done is we've used the design principle of composition. Okay, so gumball machine composes these states, okay, and we use composition instead of aggregation because, composition is a more specific form of aggregation, but here we can say composition because it doesn't make sense for these state objects to exist outside of the gumball machine. So we can say that the gumball machine is composed of these states. So we use composition, and then we also use delegation, right? Because the behavior, how the gumball machine behaves, is delegated to the various state objects. Okay, so here we've used several design principles in this design pattern. Okay. All right, so we use composition. Okay. Okay, so here is the UML diagram for the state design pattern. We have a state, right? That this is the superclass, and then we have various subclasses to the state. So here, this would have been sold out or has quarter, etc. that we saw earlier. The context here in our example, of course, is the gumball machine. Yeah, it's the class that has all the various states. And then there are these actions. Okay, it's shown here as a request. Okay, and the way the request is handled is by delegating to the current state. And of course, each of these state subclasses has to be able to, has to implement each of the actions. Okay, so here it says that the gumball machine is making a request, which is actually then invoking an action on the current state. And so the various state subclasses have to implement the code to perform the action, depending on the state. Okay. All right, so that is the state design pattern. Okay. Any questions about how this works? Okay. That this is basically a design pattern that tells us how to implement a state machine. Right? You have an object that changes state. Okay, we have the gumball machine that changes state. Each state is represented by a class. Okay, all the states are subclasses of the state base class, and each of the subclasses have to implement the actions, and each state subclass implements the actions in a way that's appropriate to that state. Okay, and that's what we saw. Okay, so let's implement the change, which was the 1 out of 10 gumballs sold is a winner, and you get an extra gumball. Okay, so now we're adding a winner state. Okay, and it's just yet another subclass of state. Okay, and okay, and then here is the winner state. Okay, now the winner state. Okay, it has a more sophisticated dispense function. So of course it has to implement all the other functions, but here's dispense, and it then takes care of whether or not you're well, here it takes care of the fact that you're a winner because you're in a winner state, and you get an extra gumball, assuming there are enough gumballs left in the machine. Okay, so remember the actions are inserting a quarter, ejecting a quarter, turning a crank, and dispense, and we're going to implement them. Implement the first three just like we did with the sold state. Okay, except now dispense, you've just sold a winner, and therefore you can get an extra gumball. Okay, all right, and now how do we get into the winner state? Okay, well, we use random numbers so that 1 out of 10 times potentially 1 out of 10 times you can be a winner, and that happens in the has quarter state, okay? And when you're in the has quarter state and you turn the crank, um, uh, you could just go into the sold state as before, or you could go into the winner state, okay? And that depends on the random number generation, okay? Okay, so we were able to handle that change in a straightforward way. We didn't have to rewrite a lot of code. Okay, certainly we added a new state. Okay, and then we made a change to a has quarter state to allow a transition potentially into the winner state. Okay? And so that's what we're seeing here. Either we transition into the sold state as before, or we can transition into the winner state. Okay? But the other states do not change. Okay? And so unlike the first design, where we would have had to go into each of the action functions and add another if statement to check to see if we're in a winner state. Here, we have done a much better job of encapsulating the change of the added requirement. Okay. All right, so here is another test run of the program, and I won't go through it all again, but I do want to show you. Okay, so now I can close off the original Gumball program. Let's see, close project, and we can look at the winner version. Okay, and so okay, so here you can see that I have all the various states. Okay, so here is state.h. This is the base class, and you can see that we have 4 virtual functions here, 4 abstract functions representing the actions. And so these actions have to be implemented by the state subclasses. Okay, and then here is state dot, here's the, okay, so all I have here in the implementation is the overload. Okay, now let's take a look at one of these. How about has quarter state? Okay, has quarter state, of course, is a subclass of state. Okay, and we have to implement each and every one of the action functions. Notice that we do have a pointer to the Gumball machine, which we initialize when we construct the state object. And this one in particular also initializes the random number generator that we'll be using. Okay. And then here is the has quarter state implementation. And you can see that its implementation of each of the actions, functions, depends on the fact that it is the has quarter state. And so you can insert another quarter. You can eject a quarter, okay? And when you eject a quarter, then of course you make a transition to the no quarter state. And so we're telling the Gumball machine, now you have to change your state, okay? And for the turn crank action, then we are going to dispense the Gumball. And here we're checking to see whether or not you're a winner. Okay, and so we're doing a random number generation here. And we either transition to the winner state or we transition to the sold state. Okay. Okay. And then all the other functions or all the other state subclasses are similar. Okay, so let's take a quick, here's no quarter. And again, we have to implement all 4 of the action functions. And the only one that makes sense if you're in the no quarter state is to allow inserting a quarter, in which case we tell the gumball machine, now you have to transition to the has quarter state, and then all the other actions don't make sense. Okay? So you can see that the transitions are made by telling the gumball machine. Okay, so let me show you the gumball machine. Okay, so the gumball machine itself has the various states. Okay, are pointers to the various states, and then the set state is where we go ahead and change state. So you saw how the various state classes could tell the gumball machine to change state. Okay, and basically all that's doing is changing the state variable to point to a different state object. Okay, and so we're using polymorphism here when we tell the gumball machine to take a particular action. Well, the action is going to be determined by the current state, and using polymorphism, the action is going to be invoked on the correct state object. Okay. All right, so you can see how these design patterns are all built on top of things that we've seen before. You know, polymorphism, coding to the interface, delegation. So as I said, the design patterns are really at the top of the ladder when it comes to doing design. Okay? So if you're in a design meeting and you are working on some software architecture where there are different states and state transitions and a given set of actions, but then how each of the actions behave depends on the current state, then that is an ideal situation to apply the state design pattern. Okay? And as I mentioned before, if everybody in the design meeting is familiar with these patterns, then basically if you say, hey, let's use the state design pattern here, then everybody will know what you mean. And then you can continue discussing design at a high level, as opposed to then, you know, you don't have to go into the details of explaining what you mean by or how you would implement the state design pattern if everybody is already familiar with it. Okay. All right. Any questions at all about the state design pattern? Okay. It's I would say it's pretty obvious when you should use it, as I just explained. But I think the other design patterns are you know, once you know the patterns, it's not hard to recognize when the patterns can apply. And remember, I mentioned that, you know, design patterns are definitely not cut and paste code. They are ways to solve these common problems. And so a very common problem here is you know, an object that can change state and its behavior depends on what state it's in. Then you implement the state design pattern, but then of course you have to customize that pattern to your application. Okay, you're not always going to be doing gumball machines, presumably. Okay. Okay. Any questions at all? Okay. So next week, no wait, today's Thursday. Next Tuesday, I'm going to give you the last design patterns that I want to cover. I mentioned that in the original Gang of Four design patterns book, I think they described like 23 patterns. And I believe I've covered the most popular ones. Although in past semesters, when I've looked at the projects that the student teams have done for this class, of course, in your report, you're going to mention the design patterns that you use. I've noticed that some of the teams have gone on and looked at some of the other patterns and have found one or two of the other patterns to implement, and that's perfectly okay. I think there was one called the bridge pattern that a couple of teams decided would be appropriate for their project. So I don't want you to limit yourself just to the dozen or so patterns that I'm covering. There are others that are also very useful, and I just don't have time to cover all of them, but hopefully I hit on the most useful and the most popular ones. Okay. And your last assignment will be to try to recognize design patterns. I forget exactly how I worded it, either in rock, paper, scissors, or even in the project that you're working on, if you can. I think I asked for three design patterns, and you just describe, okay, here are the three patterns that we have used or we're planning to use, and then you say a little bit about how you're actually going to implement that pattern in your code. Okay, so that's your last assignment. But then, of course, in your final project, I will be looking at the code to make sure that you've done a good job of using design principles, and I'll be looking for what design patterns you've implemented. Okay, so I do expect you to make use of these principles and patterns, and hopefully in all your future programming projects. Okay, and any questions at all about this pattern? Okay. I have to say, these are my favorite patterns, the ones I'm giving you, so I'm kind of biased. Okay. Any questions at all? Okay. Then if there are no questions, then I will sign off, and we'll be looking at your GUI versions of rock, paper, scissors, and hopefully you all learned WX widgets well enough to then use it for your final projects. Okay, then if there are no questions, I'm going to sign off. Okay. Thank you for coming.